Alright guys, today's video is going to be a much longer one. I'm going to be going through the ultimate guide to sketching almost any graph, okay? So this video is going to be split into kind of two sections. Section 1 is aimed at just sketching graphs that you need to know for A-level. So nothing too crazy, no weird sort of graph properties that you need to know, although I will be going through some that I think are useful. And then the second part is going to be mainly focused towards interview prep, so graph sketches that you might have to perform in an interview and beyond A-level. So we're going to be looking at stuff like L'Hopital's rule, for limits, when it works. I've got some notes next to me about asymptotic equivalence and some other good things as well. So let's get straight into this one. This is going to be a bit of a longer video, so do stay tuned. But I would recommend watching the video in chronological order because all of the tips sort of build up to each other, and I've put a lot of thought into the order in which I'm gonna deliver the information. So yeah, let's start off with the A-level. So for A-level, there's a couple standard graphs you need to know. So I'm expecting that you know these graphs. So we've got y equals log x, the natural log of x, so it's going to go like that, and crosses at 1. You've got your trig functions, so sine x and cosine x. Why is it doing that? So that's sine x, and obviously cosine x. Okay, you've also got, so this is cos x. You've also got, what are the other ones? Y equals 1 over x. So like this, y equals 1 over x. And y equals e to the x. Again, standard graphs, you should know what all of these look like. And noting that y equals e to the x has a horizontal asymptote at y equals 0. Okay, so speaking of asymptotes, we're going to look at asymptotes. So this next section is focused on asymptotes. I hope I spelled that correctly. So, asymptotes, we've got 3 types. Most of you have probably heard of the first 2, but not many people at A-level hear of the third one. I don't think it really comes up at A-level, but it might be useful to know. Definitely useful to know for the people that are looking at the second section. So let's get straight into it. So we've got horizontal asymptotes, vertical asymptotes, and oblique asymptotes. These are also known as slant asymptotes, but the formal word is oblique asymptotes. So horizontal asymptotes, well, let's have a think. When do we get horizontal asymptotes? Well, we get horizontal asymptotes when our function is not defined at some point, right? And it's concerned with the y value. So, for example, we had y equals e to the x. That has a horizontal asymptote at y equals 0, simply because e to the x is greater than 0 strictly for all x in the reals, right? If you raise any real number, let's say n, to the power of any real number, that will always be greater than 0 strictly. So the graph of y equals n to the x will always have a horizontal asymptote at y equals 0. And then vertical asymptotes, you're also probably familiar with. Vertical asymptotes, for example, if I drew the graph of y equals 1 over x minus 1, that's going to have a vertical asymptote at x equals 1, right? So here it's going to look something like this. And this one's also going to have a horizontal asymptote at y equals 0. So if we just draw that. And you can notice that this is just a transformation of the graph that you should all know and love, y equals 1 over x. And later on, we're going to be looking at the behavior at and near asymptotes of different functions. So yeah, we get vertical asymptotes due to division by 0. So if you have a rational function, so you have y equals f of x over g of x, right? We have a vertical asymptote at a if g of a is equal to 0. Right? So in our case, g of x is equal to x minus 1. So we have an asymptote at g of 1 because g of 1 equals 0. Right? And that makes sense. And then we'll get onto oblique asymptotes later on. So now we're going to talk about behavior near asymptotes. And I'm going to start to introduce the concept of limits later on. But it is useful to know about limits. But it's not a necessary condition to understanding what I'm about to relay. So let's analyze the graph of y equals 1 over x. So we know we have vertical and horizontal asymptote here. Okay, so we've got a vertical at x equals 0. That's our division by 0 here. And then we also cannot have y equal to 0, because the only way that you have a rational function equal to 0, right, is if and only if the numerator is equal to 0. But 1 does not equal 0, ever, right? This is always a true statement. And so our graph of y equals 1 over x can never equal 0. That's why we have that horizontal asymptote there in the line y equals 0. So let's look at the behavior near our vertical asymptote. So there's kind of two things to notice here. One is that if we approach the asymptote from the right, our graph tends upwards to positive infinity. But if we approach the asymptote from the left, our graph tends downwards to negative infinity. Now, this is really important when you're sketching graphs, because you might have a graph like y equals 1 over x squared, where it tends towards the same value at your vertical asymptote. So the graph of y equals 1 over x squared is going to look like a bit like 1 over x, but this part's flipped, right? This is an example of an even function, which we'll touch on later on. But our graph of y equals 1 over x, if we approach it from the left or from the right, right, we get different values of our limit, right, of our function when it approaches that limit. So let's analyze kind of why this happens. Well, if I look at y equals 1 over x, if I'm thinking about x positive, so this is where x is positive, I know that my function is going to be positive, y equals 1 over x, simply because 1 is always positive. And so if I divide it by another positive number, I'm going to get a positive result, right? And so as I get closer and closer to 0, I'm essentially getting 1 over a very, very small number, a number let's say 1 over a for a much, much less than 1, that's going to result in a very, very large value, right? A large positive value. And that's why my graph tends upwards to positive infinity if I approach the limit from the right. Now, a similar argument happens if I approach the limit from the left. So 1, like we said, is always positive. And if I approach from the left here, this is for x less than 0. So this is for x negative, right? And so when x is negative, I see that I have a positive divided by a negative. So I'm going to get a negative result. And that's why my graph tends downwards to negative infinity. Okay. Now, this is really useful fact to have. And this is going to be helpful for sketching graphs of rational functions when we're trying to evaluate some behavior near 0. So yes, let's have a look at properties of odd and even functions is next up. So we're going to look at properties of odd and even functions. Okay, so we say a function f is odd if f of x is equal to minus f of minus x. I'm going to show you some examples of odd functions, and you'll kind of see what I mean. So my favorite odd function is y equals sine x. So now odd functions have the property that they have rotational symmetry about the origin, right? So, oh, why is it doing that? So what do I mean by this? Well, essentially, if you imagine what do I mean by this? Essentially, if you imagine this part of the graph being rotated 180 degrees about the origin, it would look exactly like the left-hand side of the graph, right? Or in other words, if f of x equals minus f of minus x, that means minus f of x equals f of minus x. So for example, if I have my x here, this would be my f of x. So my minus f of x would be down here somewhere, minus f of x. Oh, I don't know why yep. So my minus f of x, and minus x would be here, right? So these values are related in this way by this relation. And that gives us an odd function. So what about even functions? We say a function f is even if f of x equals f of minus x. So our favorite even functions, y equals x squared, or another one, y equals cosine x. So let's analyze this relation here. So we have f of x equals f of minus x for even functions. That's a bit easier to see. So if we have x here, and if we have minus x here, those two things are equal. Okay? Now that gives us some nice integral properties, because we can start to we can integrate functions and know the value of those functions very easily if we know the function is odd or even. So for example, if I have the integral of f of x dx from minus a to a, and let's say f is an odd function, this integral will always be equal to 0. Why? Let's have a think. Well, we know that integrals take into account, the sign of the area under the graph. So for example, if we have, let's have an odd function, let's say y equals x cubed, and if I evaluate that integral from minus a to a, let's take a positive real, this area here is going to be exactly the same as this area here, only this area here is negative and this area here is positive. And so when we take the integral from minus a to a, this integral will always evaluate to 0. Now, what if we took the integral from minus a to a, that is a very large integral sign, of an even function? So let's take y equals x squared. Well, this area here is exactly the same as this area here, and they're both positive. Therefore, this integral is going to be equal to 2 lots of the integral from 0 to a of f of x dx, because I just have 2 lots of the same integral. Hopefully that makes sense. Okay, now we're going to be looking at limits of functions is next. So limits of functions and evaluating limits. Okay, so we already spoke about evaluating limits for y equals 1 over x, and we knew that we had to consider the limit as x approaches 0, but from 2 different directions. So the way we denote this is 0 with a little plus of 1 over x, and we say that is equal to infinity, positive infinity, and we say that the limit as x approaches 0 from the negative side is equal to negative infinity. Okay? So let's say we wanted to evaluate the limit as x approaches infinity of 2x plus 3 over x minus 1. This limit is a little bit trickier, right? We've got to consider maybe this vertical asymptote here. We've also got a rational function, and we've got this 2x plus 3, x minus 1. Well, I should really be putting a little plus here. Let's consider the limit as x tends to positive infinity of this function. Well, when we're evaluating rational functions like this with polynomials as our numerator and denominator, we need to think about higher order and lower order terms. So as x tends to positive infinity, the contribution of this minus 1 and this plus 3 in relation to 2x and x is very, very small. What do I mean by this? Well, when x gets very, very large, this minus 1, essentially the percentage difference between x minus 1 and x when x is very, very large, right, essentially tends to 0, right? The percentage difference is so incredibly small that they're practically the same thing. So in our limit, in our approximation, we would say that this limit is actually equal to the limit as x tends to positive infinity of 2x over x. And so this limit is equal to 2. Right? We have a really, really large number being multiplied by 2 and then divided by that exact same very, very large number. So our limit will approach 2. And that's why this graph will look a little bit like this. It will have a horizontal asymptote at y equals 2, right? And then we'll have our vertical asymptote at x equals 1. So let's put that in. There's 2 there. And our graph will kind of look a little bit like this. Okay, and you can notice that this kind of looks related to the graph of y equals 1 over x. You may be wondering, okay, why does it tend down to positive infinity here? Well, think about what we spoke about before. Now we don't have x as our denominator. We have x minus 1. And so when x is less than 1, we have that our denominator is negative. So we'll have a numerator that is positive divided by a denominator that is negative, right? As we get closer and closer to 1. And so we tend to negative infinity, right? Yep. So, for example, we can extend this idea. If we have the limit as x tends to infinity of x cubed over a whole load of zeros, x squared, right? Even though I'm dividing by a really, really, really large number initially, right? As x tends to positive infinity, this graph will grow much faster than the graph of, I don't know how many zeros this is, x squared, right? Let's take a little bit more of a simpler case. So for example, if I have the limit as x tends to infinity of x cubed over, let's go with, no, let's do this. Let's do the limit as x tends to infinity of e to the x over x squared. And I can tell you now that this limit is going to be equal to positive infinity. Now, why is that? If we look at the two graphs that make up our rational function, so e to the x and x squared, let's just consider x greater than 0 for this example. So we have our graph y equals x squared. It's going to look something like this. Now, e to the x, right? E to the x increases much faster than y equals x squared. So here we have y equals x squared and y equals e to the x. So if we choose any x coordinate, right, y2 is always greater than y1. And so because e to the x is always greater than x squared, at least for x greater than 0, when we approach the limit of e to the x over x squared, as x tends to positive infinity, the contribution of e to the x is much, much greater than x squared. And so this is going to tend to positive infinity as x tends to infinity. you're having a really, really large number as x tends to positive infinity, divided by still a fairly large number, but not as large as the numerator. Hopefully that makes sense. And now I wanted to do have a short look at end behavior and oblique asymptotes. So end behavior, oblique asymptotes. Okay, now earlier I talked about vertical asymptotes and horizontal asymptotes, and I mentioned a third, that's oblique or slant asymptotes. Now I want to introduce the idea of asymptotic equivalence. So I'm going to demonstrate this by the graph of y equals 2x squared minus 7x plus 6 divided by x minus 3. Now this graph is quite tricky to draw, to sketch, sorry. I will admit it is quite tricky to sketch, but once you've learned about oblique asymptotes and how to find them, you'll have a much better understanding of how to sketch graphs like this. So I have this rational function here. I'm going to perform polynomial long division on this here. So we're going to have x minus 3, 2x squared minus 7x plus 6. Divide this by x, I get 2x times, get 2x squared, get minus 6x here. Take away, what am I going to get? I'm going to get plus 6 by minus 7x. So I get minus x plus 6. Divide, I get minus 1. Times by minus 1, I get minus x. Times that, I get plus 3. Take away. I end up with, what's this going to be, 3. So this is equal to 2x minus 1 plus 3 over x minus 3. Now this is very important, because if we consider the limit as x tends to positive infinity of 2x squared minus 7x plus 6 all over x minus 3, that is equal to the limit as x tends to infinity of 2x minus 1 plus 3 over x minus 3, right? Now this is going to tend to positive infinity. Now why is that? Well, because we know that x minus 3 is going to tend to positive infinity as x tends to positive infinity. So 3 over x minus 3 will tend to 0. So this will tend to 0. The contribution of the minus 1 compared to the 2x as x tends to positive infinity is negligible. And so we'll just have 2. And so we'll just have 2 essentially multiplied by positive infinity, colloquially. And so this will tend to positive infinity. Now,
hello. What? What is it? Can I get something?
now this part of the graph here, 2x minus 1, is very important. This is going to be our oblique asymptote. So we're going to have an oblique asymptote at y equals 2x minus 1. So we say that, and we know if we were going to sketch this, we have y equals x minus 3. So we're going to have a vertical asymptote at x equals 3. Don't know why that happened there. Let's get rid of that. Oh, it doesn't want to get rid. Okay, we'll keep it. And then have here, so y equals 2x minus 1, it's going to look something like this. In fact, I should do it dashed. Right? Our graph is actually going to look something like this, right? And we say that our function is asymptotically equivalent to y equals 2x minus 1 as x tends to positive infinity and as x tends to negative infinity. So that's an example of an oblique asymptote. Now, we only get oblique asymptotes for rational functions when the highest order of our numerator is exactly one more than the highest order of our denominator. So for example, y equals x cubed plus 2 over x squared plus 7x plus 9. This will also have an oblique asymptote because the highest order of our numerator, right, is 3, and the highest order of our denominator is 2, and they have a difference of 1. If we had a function like y equals x to the 4 plus 5 all over x squared plus 9x plus 2, this would not have an oblique asymptote because the difference in the highest order of our leading terms here is 2, and 2 does not equal 1. So that is the conditions for an oblique asymptote, and that's how we can find oblique asymptotes, by using polynomial long division. Okay, now I'm just going to do a quick section on modulus functions, because I think the way that it's taught at A level is a little bit silly. It's not really showing the full picture of what the modulus function actually is, and the way that I'm going to describe it can hopefully help you guys to solve harder modulus function questions and graph modulus functions. So we say that the modulus of x is equal to, now the modulus function is a piecewise function. It's going to be x when x is greater than or equal to 0, and it's going to be minus x when x is less than 0. What do I mean? So the modulus of 6 is going to be equal to, well, 6 when 6 is greater than or equal to 0, and minus 6 when 6 is less than 0. But 6 is not less than 0. Therefore, the modulus of 6 is just 6. Now, where this definition comes in handy is when this input is not a number. So, for example, if I had x plus a, well, the modulus of x plus a is going to be x plus a. Now I replace x with x plus a when x plus a is greater than or equal to 0. So that means when x is greater than or equal to minus a. And it's going to be minus x plus a when x is less than a. Minus a, sorry. Okay? So hopefully this new definition makes more sense. So now if we have the general modulus function at A level, they look like this. So you'd have x plus b plus c. And we want to find out how to graph this function here. Well, if we consider x plus b, the modulus, it's going to be x plus b when x plus b is greater than or equal to 0. So that's when x is greater than or equal to minus b. And it's going to be minus x plus b when x plus b is less than 0. So when x is less than minus b. So if we wanted to extend this definition to help us graph y equals a times the modulus of x plus b plus c, we can say a times the modulus of x plus b plus c is going to be equal to, well, actually, Yeah, so let's do that. A, lots of x plus b plus c when x plus b is greater than or equal to 0. So that's when x is greater than or equal to minus b. And it's going to be minus a lots of x plus b plus c when x plus b less than 0. So x is less than minus b. So now what this is saying is that essentially when we graph the function y equals mod a times mod x plus b plus c plus c, let's say b is positive, when x is greater than or equal to minus b, we graph this function here. So we graph y equals ax plus ab plus c. Okay, so that's going to be, and when x is equal to minus b, we see that in both cases, we just end up with c. So this vertex here is going to be minus bc. But for x greater than or equal to minus b, we graph y equals ax plus ab plus c. So this is going to be ab plus c. Okay. It's going to be our y-axis here. And then when x is less than minus b, we graph this function here. So we graph y equals, and here a, b, and c are positive. So minus ax minus ab plus c. Right, and if we were to extend this, down here would be minus ab plus c, but obviously we only want this part because we're taking the modulus. So hopefully that newfound understanding of modulus functions and how they work can help you tackle harder modulus graphing. What is next? Okay, so now that we're done, I'm going to move on to graphing some A-level examples using some of the techniques that we spoke about earlier. Another example, say we wanted to graph y equals e to the x squared. Well, I know how to graph e to the x. I know that it has a horizontal asymptote in the line y equals 0. I know that it tends off to positive infinity as x tends off to positive infinity, and it tends to 0 as x tends to negative infinity. Maybe I can use one of the properties that I talked about earlier, because I noticed that when I have an x squared here, this is actually an even function. And so f of x is equal to f of minus x, right? And we can test that. Let's say f of x is equal to e to the x squared. F of minus x is going to be equal to e to the minus x squared, which is equal to e to the x squared. And so f of x equals f of minus x, which means this is an even function. So what does that mean when we're graphing this? That means essentially when we graph e to the x squared, whatever happens to the right of the y-axis must also happen to the left of the right axis. In other words, there is reflectional symmetry in the line x equals 0. Okay, well, when x is equal to 0, I know that e to the x squared is going to be equal to e to the 0, which is 1. And so I know that it's going to cross my y-axis at the point 0, 1. So I can mark that on. Oh, nice, my connection restored. And then I know that it's going to have a similar exponential shape. Obviously, this isn't going to be to scale. And I know that when x tends off to positive infinity, my e to the x graph shoots up to positive infinity. And likewise, I don't have to think too much about what happens on the other side of the y-axis because this is an even function. So it's going to look like this. Oh, like that. Let me draw that a bit better. So almost like a parabola. Right, and this is the point 0, 1. It's our x-axis, this is our y-axis. So let's say I wanted to graph y equals 3x plus 5 all over x minus 2. Well, a couple of things to notice here. One is that we're going to have what kind of asymptote? A vertical asymptote here at x equals 2, because we can't have division by 0. So we already know we can add that in. So where is that? So let's say our 2 is here. This is our x equals 2. Now let's start to think about the limit as x tends to positive infinity of 3x plus 5 over x minus 2. Now remember what we said about the contribution of terms that aren't of the highest power. So not the leading coefficient. We only care about the leading coefficient when we take our limits here. And we see that the contribution of the minus 2 and the plus 5 is negligible as x tends to positive infinity. And so this limit is going to be equal to 3 by what we discussed earlier. And so we're going to have a horizontal asymptote in the line y equals 3. Now let's think about the behavior near these asymptotes. So we know as x tends to positive infinity, our function is going to tend to 3. Is it going to tend to 3 from above or below the graph? Well, let's have a think here. When x gets very, 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 very large, this numerator is going to be larger than the denominator, right? And so because the numerator is always larger than the denominator, this quotient is always going to be greater than 3, even as it approaches the limit. So we know that as x tends to positive infinity, this quotient here is going to tend to 3, but the numerator is always going to be larger than the denominator. And so the quotient is always going to be greater than 3, right, as it approaches the asymptote. So we know that our asymptote is going to approach from above. It's going to look something like this in its end behavior. And then as we get closer and closer to 2, from the positive direction, right, we have 3x plus 5, well, that's clearly going to be positive for x greater than 2. And then for x greater than 2, we have x minus 2 is also positive. But we have a really, really small denominator, because as we approach 2, so imagine we have like 2.00001 for x minus 2, that's going to be 0.0001 compared to whatever this numerator is. That's going to give us a really, really large number. So we know that our graph is going to tend off to positive infinity up here. And likewise, by a similar argument, we can draw the other side of the asymptote. So when we consider as x tends to negative infinity, well, the same applies, right? As x tends to negative infinity, this here will also tend to 3. Y will also tend to 3 because we will essentially have a large negative over and also a large negative, but this large negative is going to be 3 times this one, right? And so our graph is also going to tend to 3 from the other side. So let's try and graph that. So it's going to tend to 3 here. It's going to tend to 3 here. And then, started bending a bit too much. And then by a similar argument, our graph's going to tend down to negative infinity. Why? Well, because when x is near 2, but from the left-hand side, this denominator is going to be negative. And so we're going to be dividing by a really, 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 really small negative number. Apologies for the coughing. And so our quotient is going to tend to negative infinity. And that's why the graph looks like that. Okay, nice. Our next graph is going to be y equals 2 plus ln 1 plus x. So we notice that this is just a transformation of one of the standard graphs we should know at A level, which is y equals ln x. So y equals 1 plus ln 1 plus x. Well, I know that my graph of y equals ln x, this is 1 here. I know I have a vertical asymptote at x equals 0. So if I shift it by 1, that means my graph's going to get shifted 1 unit to the left, right? So I'm going to have a vertical asymptote here at x equals -1. But then I'm going to shift my graph up 2 units. So it's going to look something like that. And it's not going to be to scale. And you can figure out what this is going to be. Well, when x is equal to 0, you get 2 plus ln 1. But the natural log of 1 is equal to 0. And so this is equal to 2. Okay, so that's our graph y equals 2 plus ln 1 plus x. All right. Thanks for sticking through this part of the video. I might actually split this into 2 parts because I've realized that it's going to be really, really long. And so I will be releasing a part 2 of these videos, and part 2 will be focused on interview sketching and sort of much more useful ideas when it comes to drawing harder graphs, such as y equals sine squared, x over x squared, and y equals e to the 1 over x squared plus 7x plus 12, and stuff like that. So stay tuned for that. Apologies for my voice, I am quite sick. Hope you guys enjoyed this video. I'll see you in the next one.